Let us go through some important properties of electric field lines. First, electric field lines always originate on a positive charge and terminate on a negative charge. Sounds fancy? All with diagrams and everything? It's pretty obvious actually. We decided that electric field is actually electrostatic force per unit test charge. Clearly, if I have a positive charge, the direction of the field will be pointing away. And if I have a negative charge, the direction will be pointing towards. That's the reason why electric field lines originate from a positive charge and terminate on a negative charge. Focus your attention on especially the diagram D. Can you see a positive charge and a negative charge in the vicinity of each other? Can you see how because of this very property, I can justify formation of these closed loops? Right? Perfect. Next property. The number of lines leaving a positive charge or ending at a negative charge is proportional to the magnitude of the charge. What does it mean? It means, can I actually physically count the number of lines? Or is there a restriction on the value of charge is allowed that many number of lines to represent? No. So, example 1 coulomb charge, if I have chosen to draw 6 lines coming out of it, am I okay? Am I allowed to do that? Yes, you are. Example number 2, the 4 coulomb charge. What I have chosen here is 8 electric field lines originating out of the 4 coulomb charge. Am I allowed to do that separately? Yes. We are allowed to actually draw example 1 and example 2 in isolation. We are correct independently. But the problem arises if these two cases are taken simultaneously in one example. What do I mean? Means if I have chosen to draw electric field line diagram using 6 lines for 1 coulomb charge, then for 4 coulomb charge, I should have used 24. Do you get that? In absolute, they are fine independently. But taken together, if you choose one standard, then you stick to that. In that case, number of lines will be proportional to the magnitude of charge. If 1 coulomb has 6 lines, 4 coulomb should have 24 and so on and so forth. Got it? Good. Next one and very, very important one. How do I figure out the direction of electric field if field line is given to me? Well, tangent to a field line at any point gives us the direction of E at that point. Look at this random curvilinear field line I have drawn, and I have chosen 3 random points on that, P, Q and R. Direction of electric field at point P will be given by tangent at point P. Direction at point Q will be given by tangent at point Q, and similarly direction of field at point R will be given by tangent at point R. Understood? Field line are given to me. I can figure out direction at any point of the electric field by drawing a tangent. 2 electric field lines can never intersect. Well, a diagram is showing them intersecting. And the question is, why is this wrong? Anyone? Well, I can't hear you, but can you answer that? Fairly simple. Because if I intersect 2 field lines, you have a point of intersection. And if I ask you draw a tangent at that point of intersection, you have 2 choices. How can one value of electric field have 2 possible directions? No, it's a unique value with a unique direction. Hence, 2 electric field lines can never intersect. They never form closed loops, as a line can never start and end on same charge. Well, you see, when I drew a plus and a minus charge in the previous slide, that is not the closed loop I meant, because that was not starting and ending on the same charge. It was starting on positive and ending on negative. What I'm trying to start here is a discussion that I can't have a field line starting and ending on the same charge. It cannot. It originates from positive and terminates on negative. Good. A very nice pictorial representation of a very wonderful tip. In a region of uniform electric field, what is a uniform electric field? A region in which the magnitude and direction of electric field remains unchanged. Who does not produce uniform electric field? Point charge. Remember, In a region of uniform electric field, the field lines are straight, parallel, and uniformly spaced. By looking at the diagram, I can see, look at the density, the packing of the lines. Equispaced? Is there any change in that direction whatsoever? No. This is the best representation of uniform electric field. Right? In case of a non-uniform electric field, well, the example is right there with you. A point charge. I've taken actually two cases. One is point charge Q, one is point charge minus Q. What's the difference? Plus charge Q is having lines of forces originating from it, while the minus Q is actually having termination. Okay? In case of non-uniform electric field, you have lines which will be pointing in different directions, fairly simple. But I actually have a very important tip here for you. Are you with me on this one? Okay. What I'm trying to say here is that using electric field line diagram, can I find out the value of electric field? No, I cannot. But can I compare the values of electric field, as in which is higher, which is lower? Yes, I can. How? Look at these 2 points in either of the diagram, P1 and P2, right? P1 is closer to Q than P2, right? Electric field strength, I repeat, electric field strength is directly proportional to the density of packing of electric field lines. As in, more closely spaced are 2 electric field lines shown. More is the packing fraction, more is the value of electric field. For example, if I draw 2 concentric circles, for charge Q, can you see the space between 2 consecutive lines is lesser in circle 1 and higher in circle 2? This lack of space, this increase of space is actually signifying decrease in the value of electric field. In other words, pertaining to my current example, as I go away from charge Q, the density of lines is decreasing, hence the magnitude of electric field is also decreasing, which I already knew. Remember, E proportional to 1 by R square? But I'm saying even if I didn't, just by looking at the diagram, I can actually figure that out.